Welcome learners. Let us continue our discussion in the first chapter from the main textbook by William Hayth and John Buck. And in this lecture, we are going to talk on the coordinate systems, the remaining two coordinate systems to be precise, and that is the cylindrical and spherical coordinate systems that are widely used in locating a free point in free space. This is the last topic from the first chapter, and we'll try our best to understand this as much as possible. So we start first with the 2D system or the 2D polar system, and to get an idea that how the 2D polar system can be utilized in the 3D coordinate system. So on your left you can see a Cartesian plot, and on to your right you can see its 2D polar representation. So if I have any point in the Cartesian x and y plane, a 2D plane, let's say if I have a point 4x plus y, and if we write in terms of electromagnetic wave, so it is 4a of x unit vector plus 4a of y unit vector. So if I locate this point, it means I'm moving 4 points from the origin on the x-axis, and I'm moving 4 points on the y-axis in the vertical scale, and a point of intersection gives me this point of 4ax plus 4ay. Now if I want to translate the same thing onto a circular disk in the 2D domain, I use the polar plot representation, where normally I get the magnitude and phase of this value, which we normally call as a phasor representation. So now what's happening? So again we have the x and y coordinates, but now it is represented in new terms, or rather two new terms. So since we are moving in a circle and we want to represent the same point, which is 4ax plus 4ay, and this is our point over here. So how we can define it? So we say that if we move from the origin towards that point, we represent it as a new value of radial distance called rho. So the rho over here is basically the radius of the circle, or we call it as a radial distance covered. Secondly, since it is a circle, we need to rotate to a certain point so that we can take this point and move along any point in the circle. So in order to move or have this circular rotation or anti-clockwise rotation, we define a second variable which is known as phi, represented over here. So now what is phi? Phi is basically the angle when we move from x to y. So whenever we have a two coordinate system x and y, and we are representing a circle, whenever we move from x to y, we say this is an angular motion, and we represent it with an angle phi. So now the radius which was made earlier is connected from point x to point y, and thus this gives us the angular rotation. We can further enhance the analysis, like if we extend this point to the circle, let's say over here we call it as p dash, and the radial point will still go straight, so this becomes our p dash. But if we want to find the rotation angle, this will be again moving from x to y, and sometimes it is such that it is just crossing the circle, so it becomes a tangent to it. So the value of phi is basically the angular motion, or it becomes a tangent line to a circle. So this is what the phi is. So whenever we move from x to y, we generate this phi or angular motion in the 2D polar plots. So if we want, so this is basically analysis of a point transformation. Point transformation means we are just considering a single point in space. So this is known as a point transformation, and how we are going to transform it. If you want to convert from Cartesian to polar coordinates, we can use this expression, and if you want to convert the other way or vice versa, we basically use this equation. So this is basically the point transformation that is being utilized. Now once we understand this radial component rho and the angular motion or the tangent to the circle phi, we can move our analysis to the 3D coordinate system, and in the 3D system we call this as a 3D circular coordinate system or a 3D cylindrical coordinate system. So both names are utilized in various books, but the idea remains the same. Now in 3D coordinate system, our geometry has a new parameter. So we already know that any point in space in a 2D is represented by the radial distance rho and its angular motion phi, but we introduce a third element taken directly from the rectangular coordinate system, and that is the z-axis. So whenever these 3 points intersect, we find the location of that point P, and again remembering that all these 3 axes in any coordinate systems are 90-degree apart, or they are mutually perpendicular to each other. Similarly, once we have these 3 coordinates, the unit vectors will follow as well, which are represented as a rho, a phi and az with an arrowhead on top. So these are the 3 representations which you can use, but in our case, in our lectures, I'll be using this one with an arrowhead. And we'll look into this more shortly, but I'll just cover this slide. And another thing, that whenever we want to do the cross product between these 3 variables, so difference will give you a value which are 90-degree apart because we have a sine theta, and if you have a same value like a rho multiplied by a rho, or cross product, it will be 0 because sine 0 is 0. So this is basically the cylindrical coordinate systems. Let us study more on the axis and the unit vectors and understand the planes associated with the cylindrical or 3D cylindrical systems. So again, the idea is, if I have a point P in the rectangular coordinate systems as x, y and z. So this is the rectangular coordinate systems with any scalar location as x, y and z. It can have its own unit vectors like ax, ay and az. So if I want to locate or reach to a point over here, I need to follow a certain path. Let's say I move certain path x, I move certain path y, and then I move a certain path z to reach this position. Now if I want to reach this position in an object or in an environment which is in the form of a cylinder, how can I do that? So I'll take the same 3 axes, but this time, so originally it is x, y and z, and I want to reach the same point. But now in order to do the analysis of a cylindrical object, I will consider that my object is having a cylindrical form, which means that the point is lying on one of the cylinders. It can be on the top and the same can be on the bottom. So if I join these points, I'm making a cylinder over here. So this is the point which I want to be at in this space. So how can I reach to this point? So in order to reach this, we take the example of the 3 axis location in the circular or cylindrical coordinate system, and that is, now the variables are rho, phi and z, where rho is the radial length and phi is the angular motion. So we know the radial length if we travel a certain distance along the x-axis. So let me call this rho. So assume this is the radius of the circle, but it's in a cylinder form. Now what I can do is, I need to move from x to y. So whenever I move from x to y, we have seen in the 2D polar plot, this represents the angular motion phi. But where should I move to? Should I go completely from x to y, or should I remain somewhere in between? So this depends upon where the point P is having its image. So let's say the point P's image is created over here. Let me call this P dash. So this is the shadow of point P, and now my rotation will be from x to this point over here, which will be my phi. And then I know that the image is in a straight vertical line, so I'll just follow the z axis on top to reach to point P. So this becomes my z axis, and this is how we basically form a cylindrical, or we form a motion or movement reaching to a point in a cylindrical axis. So the things associated, or the ranges associated with the cylindrical coordinate system, is that the value of rho is from 0 to infinity. The value of phi, the angle, is from 0 to 2 pi, and the z remains the same as negative to positive infinity. So this is the ranges that we utilize whenever we are trying to plot or locate a value in space. Another thing associated with this is the unit vector representation. So unit vector representation of the cylindrical coordinate systems will be such that if so I'll stick to the green one, again draw the system. So this is y, this is x, this is z. But now before I do that, first I need to understand what are the planes of this system. So let's first understand the planes. As again we saw in the RCS system, the planes are important because the numerical problems talk about the planes or a point being in the plane rather than the specific location. So in order to understand the planes, let me try to use a different color scheme. So so now let us first make something like this. So this is my first point, this is my second point, and I join something like this, and then I make something like this. So now you imagine this to be a slice of a cake. So you have a circular, around 360-degree shaped cake, and you have cut a triangular slice, and then you have taken out the slice where the face is a cylindrical form of the cake facing you. So we say that this plane is having a value of rho which is constant. So this is an important plane. Then we want to know what is the value on the z-axis, or where the z-axis is 0. So the point over here, the top, is where the z-axis will have a constant value. So this means its value remains the same. And now what about the phi, the last coordinate? So for phi, let us assume a point P. We join this point P and we go towards the origin. So this black is basically the value of phi which remains constant. So these are the three planes inside the cylindrical coordinate system, and these are the cuts basically that we want. So let us look at one of the cut. We take phi is equal to constant value and see how we can read. So for the phi is equal to constant value, I need to have a shape something like this and something. So this is the cut, and if this is the point, so this is basically phi is equal to constant plane. The value of phi or across the 360-degree in the cylinder will remain the same. If I move from here to here, this is my phi, and this is the radial distance rho, which can be moved, but I'm just selecting a plane. Phi is equal to 0. So this is how the planes are made inside a cylindrical coordinate system, and these planes are very important when solving problems, as we saw with the rectangular coordinate system. Now what about the unit vectors associated with this? So we know that the unit vectors which make this as a complete vector is a of rho along a of phi and along a of z. So in this example, let's say if I have this point P, so its location scalar values will be rho, phi and z. Similarly, if I have the image of P dash, so it will be rho, phi and z. So where are the unit vectors at point P and P dash? So we always know that this is going to be my radial component. So we say this is unit vector a of rho because it is moving in a certain direction. So we can say if this is point rho, I can move it to this point as well, and its image is also over here. So this is a rho. What about az? So az is obviously in the opposite direction, in the vertical up. So this is az, and a phi, as we mentioned, is moving from x to y. So if we move from x to y, this becomes like this. So this is a of phi. In order to have a better understanding of this, let us have a look at this. So the first part A basically shows you the faces or the planes where the values remain constant. So I mentioned this first phase of the cylinder is where you have a value of phi is equal to a constant value. This cut vertical is basically phi is equal to constant, and on the top the triangle that we formed over here is for the z value being constant. And the unit vectors, if I select any point P, so the radial component is along the line, this is a rho, az is this one, and this is tangent to it, which is a phi. So I think this is a better representation of the unit vectors and where they are in any cylindrical coordinate system. Other thing associated with this is obviously the cross product and the dot product of it. So again, if we take the cross product of a rho with a rho itself, we take a phi with itself, and we take az with itself, so the product comes out to be 0 because sine 0 is 0. But if we have a rho into a phi, so the output is the third vector If we have A phi cross product of AZ, it comes out to be A rho. If we have AZ with A phi, it comes out to be A phi. So this is the, and all these are vectors, the representation of unit vectors in terms of the cross product. Similarly, if I take A rho with AZ, so then it is going to be negative A of phi. So you have to also keep this, remember, because it is an anti-commutative law. So these are the definitions and representations of the cylindrical coordinate system in terms of its planes or faces, its ranges, its faces, its unit vectors, and how to locate a point. So you should know these things. I have tried my best to represent it, and the images from the books are having a more clear representation of this. So now let us come to this third part of the image, and that's an important concept as well, and this is talking about the differential elements in the cylindrical coordinate system. So previously we mentioned about differential elements, which meant that how many small steps or how many small distances we can cover to reach a point, So now we are talking about the same thing but in the context of cylindrical system. So how to go about this, or how to understand the values associated with this. So let us say I want to find the differential elements, and obviously we first need to figure out what are the three differential elements that are being utilized, and once we know that, we can find the differential length if it's a straight line, differential volume if it's a cubic structure, or a differential surface if it's a piece of paper or a sheet of paper. So what are the differential elements associated? So let us assume that I have inner cylinder surrounded by an bigger outer cylinder, and the idea is the same, that I have a point P on the inner cylinder and I want to reach to another point P dash on the outer cylinder. So what's the distance that I can cover is basically in the form of a straight line, and we call this as the differential length if we are talking about the linear distances. So this means that we will have the axis location as rho, phi and z, and P dash will have the axis location of rho plus d rho, phi plus rho d phi, and z plus dz. Now where does this rho comes in the second expression, we are going to look into this, but for the time being assume these are the coordinates between P and P dash, and this is where we want to go. So now what happens is, if I draw a complete diagram, or we complete the lines connecting P and P dash, we find that this is basically forming a cube. So this is basically a cube that is being formed over here. So how can we go about solving this cube? So in order to solve this cube, let us consider the top view of the cube and see what it looks like. So again, let us say I'm taking the top side of a cube between P and P dash. So it will have a certain representation like this. So I have this portion, and then I have the representation as such. So this is basically a stretched out cube if I am looking at the top side from it, and this is the various faces of the cube. Obviously it has 6 faces: front, back, top, bottom, left and right. So this is the cube which I formed. Okay, let me try to make it more clear so it doesn't get jumbled up. So this is the point. So this is now the cube that I have. Now what is happening in this cube? So let me draw the complete axis on this. So let us say this is my x, y and z. So this is my z, this is my x, and this is my y, and let us assume there are few things extracted from here. Okay, so this portion is basically the back of the cube, and this portion is basically the front of the cube. Okay, so now we want to understand where the differential elements could be and how I'm getting the value of p dash, especially this term over here. So if we look at the axis and try to figure out where the rho could be, so we know that rho is always a radial component that is moving away from the z-axis. So this is my d rho, the radial element, as we saw previously over here, that d rho is something which is moving away from the z-axis. Then what about d phi? D phi is always when we move from x to y. So we know this as well. So movement from x to y is this portion. So this is going to be my d phi. But what is the object that is being moved? Obviously the object that is moved is rho. So if rho was a point or the radius, then this is the radius that is being moved. That's why we have introduced rho d phi in this equation. And finally we want to reach a point. So let us say that this is the p dash where we want to reach, and this was the p point on the back, and the distance between these two was something that we want to find, like d of L. So now d rho was the point outward from z-axis, d phi is the rotation, and then this point will be d of z. So this is how we get the three differential elements for the cylindrical coordinate system, and that comes out to be d of rho, then you have phi, d of phi, and finally the element of d of z. So these are the three differential elements that we need to remember in order to find the differential length, volume, and surfaces. And the cylindrical image which I showed over here is the explanation of these unit vectors or the differential elements. Now once we have these, we can easily find the differential length. So the differential length can be easily found, which is d of L, which is the distance vector from p dash to p. So dl comes out to be, so I'm writing the final form, d rho a of rho plus rho d phi a of phi plus d of z along z-axis. So this is the d of L, or the differential element in terms of cylindrical coordinate systems. We can also take its absolute or magnitude value as well, which comes out to be d of rho square plus rho d phi whole square plus d of z whole square. So this is the representation of the differential length. What about the differential volume? So differential volume comes out to be just the multiplication of length into width into height, which is all these three elements. So just I write it in the form of the book, which is d rho d phi multiplied with d of rho multiplied with d of z. So this is the differential volume. And finally we have differential surface. If we are finding any point in on a piece of paper or on a sheet, we basically take it as d of s is equal to its standard equation, d of s with the dot product with the normal vector. So d of x along rho, d of s along phi, and d of s along z. It comes out to be, so again if you are working for d of rho, you just block this element and take the remaining elements. So it comes out to be rho d phi multiplied with d of z, and the unit vector is a of rho. Similarly for d rho phi, you block the second element and you introduce the remaining elements. So d of rho, d of z, and the unit vector will be a of phi. For the third one, it comes out to be rho d of phi with d of rho, and the unit vector will be a of z. So these are the three surface or differential surface representations if we are working in the cylindrical coordinate system. So now let us look at various transformation techniques when we are working with cylindrical coordinate system. Like if we are given any vector a in the Cartesian coordinate system and we want to see its conversion in the cylindrical coordinate system, so how we can go about it? So there are two ways to solve this. The first way is based on steps method and the other is based on the matrix representation. So I'll do the steps method and I'll give you the equations for the matrix representation. We can have a look at one of the solution to the matrix. But let us first start with the steps method. So the step method says you basically are given any vector A, you represent it in the unit vectors of a rho, a phi and a z, which means whatever you vector you are given, you distribute it into its components, scalar and vector. So A is broken into these components and you multiply it with the unit vector in which coordinate you want to go, let's say Cartesian. Then again you take the second element, you distribute it into its scalar and vector components and you multiply it with the second scalar unit vector and then with the third scalar vector. Once you have done this part, you move to the second step of remembering this table, where basically this shows us the combination of unit vectors needed to solve the problem, and these combinations are basically coming from these values. So what is the output of ax multiplied or dot product with a rho, ay dot product with a rho and az with a rho, similarly for the remaining vectors. So this table is basically going to give you this, and the final step is the point transformation conversion between x to rho and y to rho, and z remains the same. So in order to test this, let us take an example and see how we can go about this. So what is the example? So this is the example. So let us say what happens. So this is straightforward. Let us say we have been given a vector f represented as 2xy a of x minus 5x plus y plus z a of z, and we want to express this in cylindrical coordinate system. So which means we are given a Cartesian system. So this is the Cartesian coordinate system. We can recognize this because we are given the unit vectors of ax and az, and we want to convert it into cylindrical coordinate system, which means our answer should be in the form of a rho, a phi and a of z, having these unit vectors. So how can we utilize these step methods over here? So the steps method is such: the first step is to represent the given Cartesian vector f with its unit vectors along with the unit vectors in which we want to convert to. So we first find f of rho, then we find f of phi, and then we find f of z. In order to do so, we take the original vector and take the dot product with the a of rho of the cylindrical coordinate system, which means we have original vector 2xy in the x-axis and z-axis multiplied or dot product with a of rho. So now 2xyz remains the same. Where does this cos phi comes? So we have to go back to the second step, where we can see that when we have a dot product of ax with a rho, we get cos phi. So you can see we got cos phi. Similarly, if we take the dot product of the second vector az with a rho, so az with a rho gives us 0, so that's why the second term becomes 0. So we are left with 2xy equals to cos of phi. Now what is the next step? So the third step, so we can say this was step 2, and now we move to the third step, step 3. The third step is we use the point transformations and input the value of x, y and z. So what is the value of x, y and z? So x is equal to rho cos phi, y is equal to rho psi phi, and z remains as it is. So now you put x, y, z as rho cos phi for x, rho sin phi for y, and z remains as it is, and cos phi comes as original value. So once you simplify it, this is the conversion into the cylindrical coordinate systems for the first value of f of rho. Same thing we do with the second row and f of z, and finally our output in the Cartesian coordinate system is such. So you can have a look and understand how we did the f of phi and f of z following the same 3 steps and remembering the table and the point transformation form. So this is how the conversion has taken place. Now let's move to the last topic and the last coordinate system from the first chapter, and that is on the spherical coordinate system. And this is a very important topic, but its values remain the same. So again it is the 3D coordinate system, and it is utilized whenever we have a shape or the surrounding in the form of a sphere. So how do we go about this? So in the spherical coordinate systems, our axis location or the scalar elements are represented as r, theta and phi. Again, r being the radial element or the radius of the sphere. Theta is basically the value or the angle from z axis to the radial point, and phi is again value or angular rotation from x to y, as we saw with the cylindrical system. So this remains the same. So so the ranges that we can have is the ranges of r will be from 0 to infinity. For theta is from 0 to 2 pi, sorry, in this case it will be pi, and for phi it will be from 0 to 2 pi. So these are the ranges that can be used to locate any point in space, in free space. So cylindrical coordinate systems are drawn. How we look into this? So for example, consider you have again to reach to a point P, and now how to do that? So we basically first draw the axis z, y and x, and let's say our point is lying anywhere over here, point P. So this is the representation of the spherical coordinate systems. So from the origin we draw a straight line. This is our radial distance. The angle which is made from z to the point is basically our theta, and when we move from x to y, this is our phi. So this is how we reach to a point of r, theta and phi in the spherical coordinate systems. Again, what are the unit vector representation of the spherical coordinate system? So if I take any point P, so the radial component is this one, which will be extended to AR. The phi component is the tangential element which is around this cone. So this is a phi, and theta is if we move from z to the point on r, so this is unit vector a of theta. So these are the unit vector representations of the spherical coordinate systems of any point in space. Secondly, its cross product remains the same. So if we have the same unit vector being cross product, so output will be 0, and if it is different with AR into A theta, so it is going to be the third element cross product. So again, similar to cylindrical coordinate systems. And again, what are the faces in the spherical coordinate system? So our radial face is obviously the front one over here. The cone that is made over here is for the theta value that is coming from the z axis. The cutout is the phi, as we saw with the cylindrical coordinate systems, and the radius r value remains the same, which is on the front side. So this is the r value. We have seen the unit vector representation. Now let's talk about the differential elements. So differential elements will remain the same. So let me go for the differential elements. So the differential elements for the spherical coordinate systems, the idea remains the same. We need to find the three differential elements. So if I have x, y and z right hand rule based coordinate system, I know that I'll change the color this time so it becomes more easy. So the coordinate system is such, if I have something like this and something like this and something like a sphere, okay. So now I can say if I have two cylinders, one is a inner, so if I have two spheres, one is a small inner sphere, other is a bigger outer sphere, and this my point is P, another point is P dash. So I can cover the distance between these two if I am considering them as a line d of L. But if I look closely, this is again forming a cube. So the cube is formed, so I need to now understand how the cube is basically working. So if I look at the cube from the top, I can say that the cube is somewhere in this location. So this is what we have as a cube, and now my point P is at the back of the cube and I want to go to the front of the cube with the point P dash. So again, the faces remain the same, but what are the elements associated with this? So point P, which is back of the cube, will have the axis as r, theta and phi, and P dash will be r plus dr theta plus d theta and phi plus d phi. So this is the location. So the differential element in terms of the distance dl comes out to be p dash minus p, which is basically, but what are the three differential elements before we go for d of l? So again, the differential elements, as you might have figured out from the main image, is the radial component is front and back. So we can say anything that is moving from the z-axis is radial component. So this is d of r. So we have d of r over here. So because radius was like this, so we can say this portion is d of r moving in the upward direction. What about the front face? So the front face is basically r d theta. So this is r d theta, and the rotational phase which is moving in this direction is basically r sine theta d theta. So this is basically what we have. So this is r d phi. So the differential element comes out to be dr r sine theta d theta and r d phi. So these are the elements for the spherical coordinate system. This means that d of l, or the differential length, then comes out to be dr a of r plus r sine theta d theta a of theta plus r d phi a of phi. What about the differential volume? So dv comes out to be, we just take the product of length, width and height. So you just multiply all these three, so you will get r square sine theta dr d theta and d phi. This is the differential volume, and the differential surface comes out to be d of s dot product with a unit vector. So d of x into r, d of s into theta, and d of s into phi. So it comes out to be r square sine theta d phi into dr. This is the differential area for radius r. Then differential area for theta comes out to be r dr d phi into a theta, and the a value phi comes out to be r sine theta dr into a of phi. So these are the values of the differential elements whenever we are dealing with the spherical coordinate systems. Now let us have a look at an example and see how we can convert the spherical coordinate systems. So for the spherical coordinate systems, again we have the steps method. The process remains the same as the cylindrical coordinate system. We need to find a of r, a of theta and a of phi. Second, we have to remember this table for the conversion between the unit vectors, and third, this is the point transformation between Cartesian and spherical coordinate systems in terms of r, theta and phi to be extracted from x, y and z of the rectangular coordinate system. So let's have a look at an example, but before that I have prepared a second method to convert between coordinates. You can have a look at them. This is the straight method where we are using matrices to solve the conversion. So you can apply any of these second steps to find any conversion. So let us take an example of spherical coordinate systems and see how it is working. So spherical coordinate systems, transformation, example. So we want to convert or transform the following vector to spherical coordinate systems. So we have been given 10a of x at p is equal to -3, 2 and 4. We have been given 10 of ay at q equals to rho equals to 5, phi is equal to 30 degree and z equals to 4. and we want to convert these into spherical coordinate systems. Okay, so how to go about this? So let us start with the solution with the first one. So in order to convert this, what we have? So we have for part A, basically if we go for the steps method, we need to find for the spherical coordinate system, we need to find A of r, A of theta, and A of phi. So these are the three things that we need to find. So how we can find it? Obviously we need to first write it with respect to the coordinate system. So basically our main equation is that A of spherical is going to be AR in unit vector of AR plus A theta with unit vector of A theta plus A phi with unit vector of A phi. So this is our grand equation or the final equation where we want the answer to be. So let me call this as our grand equation. So let us find the first step. So AR is equal to whatever we have at the coordinate system, we multiply it with the unit vector of A of r. So the coordinate system value is 10ax. So we take 10 and we multiply ax with ar. Now we are dependent on the table. So what is the value of the table? So if we go back to this table, what is the product or dot product of ar with ax? So it is sine theta and cos phi. And with the table, it comes out to be uh, let me write it as 10 sine of theta cos of phi. So this is the answer I am getting. Now what is theta and phi value? I need to know the theta and phi value. So how can I get the theta and phi value? So the theta and phi value comes from the point conversion. What is point conversion? So these are the values. So I need to find theta and phi from here. So in order to find this, I need to first figure out what is the value of r. In order to get r, I need to first figure out x, y, and z which have been provided to us. So let us first, in order to find r, theta and phi in this expression, let us first write these values for r, theta, and phi. So r is equal to x square, y square plus z square. Theta is equal to cos inverse z by r, and phi equals to tangent inverse y by x. So r comes out to be, we know the value of x, y, and z, so we only have x, which is 10, so it comes out to be 5.38. The theta comes out to be 42 degree, and phi comes out to be minus 33.4. But one thing to remember here is that in the question the value was 10ax at point minus 3, 2, and 4. This was the first part of the question, and the second part of the question is you are at 10ay at point rho is equal to 5, theta phi equals to 30, and z equals to 4. So in the first part of the question we can see that the value of x and y is -3 and +2. So if we draw the coordinate system in the 2D system, it comes out to be the second quadrant, but the result over here is -33.4, which is not in the second quadrant, rather it is in the first quadrant. So in order to move this result from the first to second quadrant, we are going to add this with 180 degree. So my answer comes out to be plus 140 6.3 degrees. So this is the phi value that we are going to use. So once we have these values, input it into this value. So A of r then comes out to be 10 sine of 42 degree multiplied with cos of plus 146.3 degree, and AR value comes out to be minus approximately 5.57 A of r. So this is the answer we got for the first value. Secondly, if I want to find A of theta, so it is going to be A of Cartesian coordinate multiplied with A of theta unit vector. So again we are going to use the table, but I'll input the values for you so you can try. A of x multiplied with A of theta. So A of x with A of theta means A of x with A of theta, so we'll have cos theta and cos phi. So it comes out to be 10 cos theta multiplied with cos of phi. We have the theta and phi value from here, so the answer comes out to be minus 5.54 a of phi. Similarly, I leave the last part for you. I'm just going to write the answer that a phi comes out to be, so this is minus 6.18 degree, and it comes out to be minus 5.54 a of phi. So my final answer from the expression of a spherical coordinate comes out to be minus 5.57 a of r minus 6.18 a of theta minus 5.54 a of phi. So this is the spherical coordinate conversion of the Cartesian coordinate system given in part A. What about part B? So again, this time we have a value of cylindrical coordinate system. So I'll just give you a hint, you can try. You need to convert these cylindrical coordinate systems into x, y and z using the point transformation method which we saw, and then you are going to find the spherical equation. So I'll write the spherical equation, final equation. It is going to be ar into ar unit vector plus a theta into a theta unit vector plus a phi into a phi unit vector, and your final answer should come out to be, so I'm going to write the answer for you to match, 3.9 ar plus 3.124 a theta and plus 8.66 a of phi. So this is the final answer you should be getting. And similarly, you can try for, let's say I'll give you another portion to experiment with. Let's say the question has a third part where you have a value of 10 az, and let's say the coordinates are r equals to 4, theta equals to 110 and phi equals to 120 degrees. So try this at home and convert the part C into the spherical coordinate system. So this will be your practice question or a take home question. And this concludes our discussion of the first chapter, where we have covered all the basics starting from vector algebra to coordinate systems to vector multiplication, and all these things are important in moving ahead to the other chapters.